the probability that t is equal to 1.5 is exactly 0. Now, why is this? It seems like it has a density value. Well, the reason this is the case is, think about it. Think about the number of values between 1 and 2. If there are infinitely many values, then that's the number of possible outcomes. Well, 1.5 only represents one of those infinitely many outcomes, and all of them are equally likely, and 1 divided by an extremely large number, especially infinity, is going to be 0. It's really, it's something that's impossible. So it's like, you know, even if you think that you're rounding to 1.5 minutes, or sorry, 1.5 years, well, it's never going to be exactly 1.5 years, right? It could be 1.4997365. These are theoretically continuous values, so there are just infinitely many possibilities. Otherwise, if they were countable, then you could say exactly how many possibilities there are. Okay, so we said that this is dealing with areas. So if I want to know the probability of a range of values, then I can find the area correspondingly under the curve. Now, first thing I'll do is I notice that this rectangular region, so again, this is the function right here. The function is, we would typically write f of x is equal to, and it's a piecewise function because it's equal to 0.25 when x is between, oh sorry, I don't want to use, I don't want to use 0.25, I want to use 1. And I'll show you why in a second. I want that to be 1, and so this up here should have been 1 as well. And it's only equal to 0.25 when x is between 1 and 2. 1 less than or equal to x less than or equal to 2. It's equal to 0 everywhere else. So in other words, right here it's 0, here it's equal to 1, and over here it's 0. So it's really a piecewise function. So to find the area, let's say I wanted to know the probability that x is between 0 and 1. Well, assuming that that's my entire set of possibilities, that area should be 1. Well, let's see. So the area of a rectangle is length times width. So this is 1 is the length, or width, or whatever you want to call it, and 1 is the length. So it's a 1 by 1 rectangle. In other words, it's really a square, is equal to length times width, which is 1 times 1, which is equal to 1. Okay, so there we have it. That's a check mark, because the overall probability of failure occurring between, darn it, I said 0 and 1. I meant 1 and 2. So the probability of it being between 1 and 2. Okay, well, what if I wanted to know the probability that the battery survives longer than, or at least 1.6 years? Okay, well, that would mean that I want to look at the area of anything greater than 1.6. I think I'm just going to draw another one. Anything greater than 1.6, this is 1, this is 2, there's the function. 1.5 is about there, so I want to know the probability of getting 1.6 or something greater, which is going to correspond to this probability, now only all the way up to 2, because technically the failure of the battery occurs between 1 and 2 years. So the probability that x is greater than or equal to 1.6 will basically be the area of the resulting rectangle. So, well, let's see, what's this dimension? That dimension is 2 minus 1.6. This is 0.4 units wide. So that would equal 0.4. Now the height of this thing is 1. So I would have 0.4 times 1, which is equal to a probability of 0.4. Similarly, I could do this for any range of values. What if I wanted to know the probability that the battery fails between 1.2 years and 1.4 years? Okay, so here's my function. Constant function at 1 from 1 to 2. Again, this is the number of years. And 1.2 to 1.4 would be about there to about there, roughly. And we want to know the area under that curve. So first of all, we know that this dimension is 0.2, some basic geometry here, and this height is 1. So this would basically be the area of that little rectangle, which is 0.2 times 1, which is equal to 0.2.